Hi, this is Martin from IEEE, specialized in telecommunications.
Hi, this is David from McGill University, specialized in power engineering. We know today the current power grid only enables one-way flow of power, typically from generators to transmission network and down to distribution network via substations. Although there are sort of communication technologies that help operating the power systems, but the communication infrastructure only covers the part between generators and substations. So it's hard to handle large-scale deployment of distributed renewable energy sources and other applications such as electric vehicles.
The next generation power grid, namely the smart grid, is characterized by a two-way flow of energy and information. The smart grid uses advanced communication and sensor technology in order to monitor and control the power grid. Typically, these two areas are studied independently. However, since smart grid is composed of a two-way flow of energy and information, it's important to show the impacts on both perspectives. So we decided to build a novel co-simulator which we introduced in this webinar.
Here it shows the topology of the distribution network used in our study. It's a modified version of the IEEE 30-node benchmark test feeder. At each node, a low-voltage residential network is connected, which represents a neighborhood area of 19 customer households. The grid has a total number of 342 households, representing a densely populated area. Depending on the penetration level, some plug-in electric vehicles will be assigned to some households. Since each vehicle can be considered as a sizable load, random and uncoordinated charging activities might cause local grid problems in terms of voltage deviation and demand congestion. That's why we need a proper communications infrastructure to help coordinate the charging activities of each vehicle, like postpone the charging to the time when baseload demand is lower.
Regarding the communication infrastructure, fiber wireless technology are envisioned to be the endgame of broadband access networks. The FiWire network can also aggregate sensor data, thus leading to our recently proposed Uber FiWire network. In urban areas, EPON networks are a viable solution. We know that one ONU can aggregate several homes by using wireless mesh networks. Where EPONs are not available, for example in rural areas, WiMAX can be used as a complementary. Here are a co-simulation model built with OMNET and OpenDSS. OMNET is an event-driven simulator and OpenDSS is a distribution system simulator. The main part is based on OMNET, which constructs a power system layer by remotely calling the power system calculator located here, which runs OpenDSS. We use HTTP in order to remotely call the power system calculator because we were running Linux in this machine for OMNET, and OpenDSS was running in Windows, so we use HTTP in order to remotely call the power system calculator. The main part of the co-simulator was written in C++ with multiple packages. The first package, the EPON package, models the OLT as well as the ONUs, the splitter, and the wavelength characteristics. The common package connects the EPON, the wireless, and the power system package. The wireless package simulates the MAC and physical radio layer. And finally, the power system package represents the IEEE 13-node network. To show some illustrative results using our co-simulator, we investigated a reactive control algorithm of PEVs. So periodically, the central distribution management system loops through all nodes. If it finds that a given node is lower than the minimum permissible limit, it will disconnects some PV with the lowest voltage profile in order to fix this critical voltage fluctuation by sending control message to these PVs. We first test data rate based sensor and we compare without reactive control algorithm. Note that we set the minimum permissible voltage limit to 0.95, located here. As shown in this figure, as vehicle connect to the grid without using reactive control, give critical voltage fluctuation. However, by sending 1 packet per second, for example, by setting lambda to 1, we reduce significantly the critical voltage duration. We also compare event-based and data rate-based sensor. With event-based sensor, packets are sent when the difference between two measurements is higher than a certain threshold expressed in percentage. With data rate-based sensor, packets are sent periodically. We note a similar result using event-based sensor with a threshold set to 0 and data rate-based sensor here. However, if we increase this threshold, for example, to 10%, we note a higher critical voltage duration here. Smart grid is all about controlling the power distribution network by using advanced communications and sensor technologies. In previous works, no significant large-scale code simulation model has been done to study the impact on both perspectives. We use Omnet and OpenDSS in order to co-simulate a power distribution network of 300 customer households by using converged fiber wireless technologies to reactively control electric vehicle chargings. We did an illustrative co-simulation comparison of event-based and data rate-based sensors. For future work, we can experiment proactive inter-home scheduling algorithms to coordinate plug-in electric vehicles in a power distribution network. Since in this study we only investigated a reactive algorithm, we can also add realistic communications traffic by using reroll trace to really have realistic conditions in the communication perspective. We can also experiment quality of service issues in EPONs and wireless mesh networks, since these networks can be used by multiple applications. To conclude, our co-simulator enables to test new proposition and really measure the impact on both perspectives.